Good morning. So today's lecture we will start a new chapter, chapter 3, circuit analysis techniques and theorem. So in this chapter you will see several sections like nodal analysis, mesh analysis. So these kind of two techniques can be used to solve electrical circuit analysis in a more organized way actually, and in more systematic way, so we can do it much easier for any complicated circuits using nodal or mesh. But this course, it's not circuit analysis. We have a lot of topics that we need to cover. Therefore, we will not discuss anything related to mesh analysis or nodal analysis. Now, we will go to some theorems that are important for us and they are also important in real life, which is Thevenin's theorem. So what's Thevenin's theorem mean? Why it is important? Basically, in Thevenin's theorem, it is summarizing some part of the circuits to be as voltage source or current source. Okay, let me just discuss a little bit some introductions about Thevenin's, then we will go to Thevenin's. So let's assume the electrical system at Auburn University. So in Auburn University, we have one, or actually more than one electrical substation. So this electrical station most likely will convert the high voltage into low voltage, or medium voltage to low voltage. So basically the outputs of that electrical signal substation, which will be around 7.2 kilovolts, something like that. Then, so we have, for example, next to parking deck of the stadium, there is one station. When you go, like the bus station, so you will see electrical substation there. Then the electricity will be distributed to all of the Auburn University buildings through underground cables. So we will not see any poles or anything there, or towers, something like that for the electricity. All of them are undergrounds. Then it will go to the buildings. So we can donate that electrical substation as a source. Keep in mind the electrical system that we have is based on AC, not DC. But here, just for shortcuts, for demonstration, I'm going to assume it as DC. AC, we haven't discussed this yet, so we will discuss this later. But let's assume it is like we can donate this by a voltage source. Then the wires, or like the electricity, will move through underground cables into the buildings. These underground cables have an internal resistance, right? From physics, the wires, internal resistance. So we will say like R wire. Then it will go to several buildings. So let's assume like we need to make it for student center. So I'm going to donate the student center by a resistance R. Then there will be another resistance for the wires, because they will be different, all the wires will keep moving. Then we'll go to student center here. We'll go to, for example, Haley Center. Then something like that, Brown Couple Center. ACLC, etc. So it will go to several things. Now, the existing system is working well. Everything is working fine. We don't have any problems with this for the electrical connection system. Let's assume currently there's a construction for the new College of Education, right? So let's assume we need, or for that project, we need to connect electricity to it. So does my system, or is my system, can handle all of these electricity or all of the loads? Which means for the new construction that we have, or the new project that we will have, can my electrical system supply this load without any problems? Or is there any problems? Like problems like what? Sometimes there is a current capacity or power capacity that we can supply. So is the power capacity enough? Is the losses is enough? Is the wires is enough? So we can do several things to make sure like if everything's all right. If not, what should I do? We will install a new power lines, maybe install a new electrical substation. So the decision of installing a new substation or new power lines, this will cost a lot. So sometimes we will say, okay, how much the maximum I can achieve to supply that without any problem? How much power, the maximum power? So if, for example, we say the maximum power is like roughly number as 500 kilowatts, and my project is 600 kilowatts. So I need to have 100 kilowatt extra. This means I need to maybe sometimes pay millions, extra millions, for that 100 kilowatts. Or I will say, I can recommend, if it is possible, to modify this project so we can save maybe 2 millions because of this. That's one application. So basically, we will say there is a new thing, which is, I'm going to call it like as RL, and I will put like arrow here, which means it's still under research, and under research. So which is basically, we haven't done this yet. We will discuss, or we are trying for, as a planning purposes, to make sure if everything's all right. Now, if we need to discuss how much power, how much currents, basically, this is the current here, I load. Let's assume all of the part of the circuits we know. We know our wires, we know the load at Brown Couple, Student Center, all of them. We already know all of the existing system. Now, we need to calculate IL. And this circuit, do you think it's easy to calculate IL? I do think it's easy because you will start from the source, then you will do KVL, KCL, Ohm's law, KVL, KCL, Ohm's law, KVL, KCL, Ohm's law, KVL, KCL, Ohm's law. So you will do this with several loops, right? This will take a lot of time. And RL is actually the load that's changing. So I want to make sure how much RL is being changed, or how much RL, for example, let me assume RL 1 ohms. Then I will see the result. How about 2 ohms? See the result, 3 ohms, and so on. So basically, I want to try to get the optimal value, which is what's the amount of RL that I need so I can achieve the maximum power. So sometimes I need to do maybe 100 times. And imagine doing this type of 4 loops or 5 loop circuits 100 times. This will be time consuming, and of course will take a lot of efforts. Even if you can do it in the computer, this will take a lot of time. Sometimes the engineering, or as engineers, our target is not only to solve the problem, it's also to solve the problem with less effort, less time, less cost. So maybe if I was like me and my colleague, if we were working on the company or working with electrical power company, and we try to do this analysis, then maybe I will be fired while my colleague will remain because he find an easier way, while my way takes several hours. Okay, so is there any easier way to solve these problems? Yes, using Thevenin's theorem. Okay, how? Thevenin's theorem says, since this part, the existing parts, it is fixed, it will not be changed at all. So this is the fixed parts. And we have the other parts, which is the changing parts, right? So the first thing, I will separate this into fixed parts and changing parts. So the fixed parts, I can denote this by calling it network A. The changing part, I can call it as network B. So the fixed part, or the current existing system with Auburn electrical connection system or University electrical connection system, I can make this fixed part, replace it by an equivalent circuit. That equivalent circuit will be a combination of voltage source and a resistance in series. This thing we will call it V Thevenins, and the other one will be R Thevenins. So we will replace that big electrical connection system to be voltage source and a resistance series. Then what will happen to the network B, or the changing part, will remain as is. Okay? Now, this circuit is much way easier than the other one, right? Now, first thing, we convert all of this circuit to be voltage source and a resistor. Then network B will remain as is, which is the same as the R load. Now, how can I calculate the analysis? Basically, you can take it as a rule for a single loop. This is single loop. Now, in a single loop, we will say the currents IL will be the voltage source divided by the sum of these resistors. This is valid if and only if we are in a single loop. So basically, it will be V Thevenins over R Thevenins plus RL. Okay? Then, if we need to do several calculations, most likely V Thevenins is constant. I'm going to assume it as A. R Thevenins is constant. We're going to assume it as B plus RL. The only changing part is RL. Now, if RL can change from 0 to 100 or whatever value, you only change the value on this expression. So instead of doing the circuit analysis, you will only substitute it in this formula. And this is much easier. So you can, instead of solving the circuit, it takes several hours, it will take you a few minutes, actually. Even like just a few minutes because of doing Thevenins, finding V Thevenins and R Thevenins, while the rest it will be in seconds. In IL over A over B plus RL. Okay? Does this make sense? So basically, Thevenins makes the life easier, especially when we do with these kind of practical problems. And when we have some new installations, we need to install new buildings, doing some analysis. Or we need to model the electrical power system that we have in certain area. So we will donate this by voltage source and a resistor in series, which is V Thevenins and R Thevenins. Okay. Any question about the overall concept? Yes?
To say in the red on the bottom right, I sub L is equal to what over V plus RC?
V, the voltage source, over the sum of the resistors.
Okay.
Yes.
I sub L is equal to D over V plus RC?
Do you mean here? I'm sorry.
In the red.
Yeah, in the red. So I assumed V Thevenins as A.
Oh, A.
Yeah, A. R Thevenins as B. So just a constant. You can see, call it C, whatever, C1, C2. Just constants plus RL. Just to make sure, insisting that the only changing parameter is RL. Any other question? Okay. Now let's go to Thevenin's theorem as a theorem itself. Now we know the application. This is one application, but actually it can be applied for several applications as well. Let's go to the theorem itself. Basically, we will replace the constant part by network A. Then network A will be a voltage source, the equivalence, which is voltage source and a resistor in series, while network B will remain the same. Network B the same, network B the same, network A, it has been changed to be a voltage source and a resistor. So we call it either V open circuit or V Thevenins. Okay? Now, the concept, now we understand the concept, and we can do any circuit like this. So just V Thevenins, R Thevenins. But the question is, we have two unknowns, which is V Thevenins and R Thevenins. How to calculate them? Two unknowns, V Thevenins, R Thevenins. So how can I calculate each one? So there are two ways to calculate them. So the first way, in calculating V Thevenins, it's fixed. I mean, two ways in calculating actually R Thevenins, not V Thevenins. So let's talk first about V Thevenins. So in order to calculate V Thevenins, we will apply something called open circuit tests. What does open circuit test mean? We will take network A, this is network A, we will take it without network B. Just make the terminals of network A as open circuits. So here is network A. Then the terminals A, B, they will be open circuits. Then plus minus, we will find V open circuits. So when we calculate V open circuits, we will say V open circuit is the same as V Thevenin. Just take the terminals, make it open circuit, find the voltage across this. The second step, which is to calculate R Thevenin, now there are two ways. So way number one, in calculating Thevenin, R Thevenin, you will take network B and apply short circuit test. What do I mean by short circuits? Take network A. Then turn off, or actually you will do the short circuit here. Connect A and B together. So what you need to do is to calculate the currents, I short circuits. So when you calculate the currents, you will calculate I short circuits. After that, you will say R Thevenin will be V open circuits over I short circuits. That's one way, by doing the short circuit test. There is a second option, and this is the second option that I like, which is make it much easier, which is by turning off the sources. Turn off sources. What do I mean by turn off the sources? You will take network A, then you need to find R equivalent across the terminals A and B. Since we have sources, any voltage source will be short circuits, any current source will be open circuits. Voltage source like this, current source like this. So, because in DC circuits, we know the elements are resistors, voltage source, current source. Voltage source will be short circuit, current source will be open circuits. The only remaining which are resistors, then find R equivalents. That's how we do it. So the procedure, we will use step number 2 for finding R Thevenin. So the first thing, apply open circuit tests to find V Thevenin. Then the second thing, which is we will turn off the sources to find R Thevenin. Then that's it. Keep in mind the general solution or the general Thevenin that's valid everywhere only when we do option 1, which is when we do find open circuit tests, short circuit tests. This is the general option that's valid anytime. While we have a special case that we can apply turn off the sources if and only if there is nothing called dependent sources. So, or something related to the practical circuit elements, practical voltage sources or practical current sources. We haven't discussed this in this course. Then when you deal with 3810 with this course, Fundamentals of Electrical Engineering, you don't need to worry about if we have practical sources, or you don't need to worry about which is turn off the sources will not work. So I'm telling you, in this course, it will be working everywhere, working well. So whenever you see in the textbook any source like coming in this diamond shape, like this, this means these sources are practical sources. We haven't discussed them, so don't worry about them. Okay? So this is the only cases that option 2, turn off the sources, will not work with Thevenin's theorem. Again, don't worry about it. What you need to know, which is find V Thevenin through open circuit tests, then turn off the sources to find R Thevenin, and that's it. Okay, how can we make the problem much easier? By doing an example, right? So we can understand or try to apply the procedure. So let's assume this circuit. Determine Thevenin's equivalent circuit at the 8 ohms resistor. Before doing any analysis, keep in mind you need to determine where is network A, where is network B. Usually, sometimes some of the problems will tell you find across the terminals A and B. or across a certain resistor. So if it says across a certain resistor, 8 ohms resistor, this means this 8 ohm resistor is network B. So this is network B. How about network A, which is the unchanged part, which is the remaining of the circuit is network A. Okay? This is very important step, so you need to know where should I apply Thevenin's theorem. Okay? Now, let's do it. Let's try to isolate them, which is basically, according to our procedure, we need to convert this to Thevenin's equivalent circuits. So we will say it will be as V Thevenins, R Thevenins, this is the equivalent of network A. Then network B will remain as is, which is here is the 8 ohms. Okay? So basically, Thevenins, we will simplify the circuits from left-hand side to be in the right-hand side. So we have V Thevenins, R Thevenins, and 8 ohms. Okay, so the analysis here will be much easier because if we need to calculate the current, the power, whatever, we will say that IL will be V Thevenins over the sum of the resistors, which is going to be as V Thevenins over R Thevenins plus 8 ohms. That's how we do it. Now, in order to solve this analysis, we need to know R Thevenins and V Thevenins. So we have two unknowns, which are R Thevenins, V Thevenins. Now, how to calculate them? Let's apply the procedure. So according to the procedure, in order to find the first thing, V Thevenins, we will make network A to apply the open circuit test. And here is the terminals A and B. So network A is inside the green circle. This is network A. We will isolate this to be at the terminal. So let me redraw the circuits. So here is 100 volts. Here is 4 ohms, 10 ohms, 7 ohms. Keep in mind 8 ohms is with network B, then we will keep it like this way. Now, my target is to calculate, here is the terminals A and B, plus minus V open circuit. So that's the open circuit test. Now, we need to calculate V open circuit, which is across the terminals A and B. How can I do it? Look at the circuits, just forget about Thevenins now, it's just equivalent circuits. Solve the circuits. The first thing, we need to assume a current directions, right? In order to assume the current directions, the currents will be out from the source. So here is I source, then I. I will split here and here, right? So do you think through the 7 ohms, is there any current flowing here to the 7 ohms? Do you think there will be currents? No. Why? Open path, right? Or open circuits. So actually, the currents here equal to 0. Then I source will keep flowing through the 10 ohms. Now, look at the 7 ohms resistor. What will happen to the voltage of the 7 ohms? V7 ohms equal I times 7, right? Which is I times R. I, we said it is 0. 0 times 7 equal to what? 0. So, since now in 7 ohms, I equals 0, V equals 0, therefore erase it, discard it. And this happens if and only if voltage is 0, current is 0. Both of them are zeros. Okay? If not, then don't erase it. So if voltage is 0, current is 0, or if there's short circuit. Here we don't see any short circuit, so just this will be erased. Okay, what should I do next? Redraw the circuits so you can get a clear image what we will do later. Here is 100 volts, 4 ohms, 10 ohms, then here plus minus V open circuits, right? So we just erase the 7 ohms. Now we are all agreeing that the current is flowing only in this loop. So here is I source, here is I source. Now look at the terminals of V open circuit and the 10 ohms resistor. So you will realize that they are the same. So the voltage of the 10 ohms is the same as the V open circuits. It's just like wires here. They are all sharing the same nodes. I mean, sharing both nodes. So how can I calculate V? The first thing, calculate I, right? After calculating I, V will be I times R. Is this correct? How to calculate I? This is single loop. And in single loop, we can say I source will be V over the sum of the resistors. So V 100 volts over 10 plus 4. And so the answer will be 7.143 amperes. Now I need to calculate V open circuit, which is the same as V Thevenin's. It will be I source times R10, which is I source 7.143 times 10. So the answer will be 71.43 volts. This is V Thevenin's. Now the first known and first unknown done. Okay, any question? Okay, easy peasy. The next thing, now we are done with step 1. Let's go to step number 2. Step number 2, we will apply the short circuit tests to find our Thevenin's. Keep in mind, step number 1 and step number 2 are independent of each other. So if you did any simplification in step number 1, this does not mean it will be applied in step number 2. Like what? You see here, the 7 ohms has been erased because both voltages and the currents are zeros. But in the step number 2, we will not do this. You will go back to the original circuits. Then step number 2 basically says that turn off the sources. Then whenever we have any current source, it will be open circuit. Any voltage source will be short circuit. So we will take network A and find our equivalents. That's what we will do. Go back to the original circuits, which is here, and look at the network A inside the circle. So how many sources do we have? 1, right? Which is the 100 volts. So this 100 volts source will be, since a voltage source is a voltage source, we will replace it by a short circuit. Is there any other sources? No. Then basically, we will isolate network A, making 100 volts short circuit, then we will find our equivalent across the terminals. So the 100 voltage source is short circuits. Then the 4 ohms resistor here, 10 ohms resistor here, 7 ohms resistor here as well. Again, we will not erase it because step number 1 it has been erased, but step number 2 is independent. Number 1 and number 2 are independent of each other. Now we need to calculate our Thevenin's here. How to calculate our Thevenin's basically is the same as our equivalents. Let's calculate our equivalents from this side. This is terminal A, this is terminal B. across the terminal. So how can I do it? Label the nodes. This is a node. This is a node. This is a node. Then according to our procedure in finding our equivalents, start from the furthest point in the observation. So the furthest resistor is the 4 ohms. Look at 4 ohms and 10 ohms. Are those series or parallel? Parallel, because the same 2 nodes, right? Between yellow and purple, yellow and purple. So we will say that 4 parallel with 10. Okay. Then what else? What's next? 4 parallel with 10. This means 4 times 10 over 4 plus 10. So the answer will be, I think, 2.85. Then redraw the circuits. 7 ohms here. 2.85 ohms here. Here is terminal A, terminal B. Let's relabel the nodes. Now we still need to calculate our equivalent here. So our equivalent basically 7 ohms and 2.85 are in series, right? Then basically our Thevenin's, which is equal to our equivalents, equals 7 plus 2.85, then it's going to be 9.85 ohms. So as a result, our Thevenin is equal to 9.85 ohms. Okay? Now I just calculated R Thevenins and V Thevenins. Remember, this is not the end. We just did find equivalent circuits. So you need to redraw the circuits, the new circuits, and write the values on it, and see if there is any other unknowns that we need to do. So now let's go back to the beginning of the question. Let's go back to the beginning. Let me give you a few seconds to write, then we'll continue. Okay. So here is the beginning of the question, which is especially here, because we stopped here, then we said we have 2 unknowns. Now we know these unknowns. So we just calculated V Thevenin's as 71.43 volts, R Thevenin's as 9.85 ohms. Okay? Now I'm ready to do the other calculation, which is to calculate IL will be V Thevenin's, which then 71.43 over R Thevenin's, which is 9.85 plus RL plus 8. So the currents will be 7.1. No, not 7. I'm sorry. What's the current will be? I think it will be 4 amperes. So this is IL, the load currents. Now let's assume also we need to do the voltage. So the voltage, V8 ohms, will be IL times the R8. So IL is 4, R8 is 8 ohms, so 4 times 8, 32 volts. Okay? So now, we calculate them in an easy way. The good thing is R Thevenin's, V Thevenin's every time is fixed. Now let's assume if the 8 ohms has been changed to be 5 ohms. Okay. What do we need to do? You will just only change them change this formula. Change it here. So it will be, I'm going to write it here just as a quick word. Okay, here. Assume R8 changed to be 5 ohms. So what will happen? You will say IL equal to V Thevenin's, which is 71.43, no change in V Thevenin's. R Thevenin's 9.85, then it will be plus 5. And in order to calculate V8 ohm, the V now it's 5 ohms, it will be as I times R, then I that we calculated there, then times 5. Okay? So no matter what it is, even if we call it, let's assume it Rx to X ohms. So it will be here as plus X, and here V of X ohms times X. And you can just substitute any value. That's the good thing. How about if the load is being changed to this value, this value, this value? You don't need to do all of the procedures, just like do this portion and that's it. Okay? Does this make sense? Any question? Again, the overall idea about Thevenin's to simplify the circuit. So we have a constant part of the circuit that's not changed, or the existing system that's not changed. Then we have the new thing or the changed parts. So the existing system will be replaced by an equivalent circuit, while the new system will remain. Then we can do several analyses on the new system. Then we can say, how about if we change this value? What will happen? Okay, just substitute in these equations. How about if we do others? Substitute in this equation, and that's it. Okay, let's do another example. Determine the Thevenin's equivalent circuits with respect to I/O and solve for I/O. Okay. So it's very important to read these kind of questions to make sure where is network B. Sometimes, maybe some questions says, will give you only network A, and it will tell you find Thevenin's across the terminals A and B. In this situation, there is network B is not given. If the question says find Thevenin's equivalent circuit across the terminals A and B, and when you look at the circuit, there is nothing connected to the other side of network A and B, then that's enough. We know network A. All of the circuits given as network A. Some of them, like as we see here, at the resistors 8 ohms, then we know network B is 8 ohms, network A is the remaining of the circuit. Now, here, we say Thevenin's equivalent circuit with respect to I/O. Now, the most important thing is to locate where is I/O here. Then the elements associated with I/O, this will be network B. What are the elements that associated with I/O? 1 kilo ohms. So that's how we determine network B. Then we will say this is network B. How about network A? Network A is the remaining of the circuits. So we will say all of this actually. All of this is network. Yeah, that one is network B. I don't know why I wrote A. So this is network B and network A. So the most important thing is to locate where is network B, while the remaining of the circuit is network A. So what we need to do is we need to calculate I/O. So our target is to convert the circuits into Thevenin's equivalent circuit, basically it will be as V Thevenins, R Thevenins, then network A, network B will remain as is, 1 kilo ohms, and IO will remain as is. That's equivalent circuits. Keep in mind IO will remain as is because network B will not be changed. Anything inside the circle of network B will remain as is. Okay? Now how to calculate IO? Single loop, right? So we will say that IO will be V Thevenins over the sum of the resistors, which is going to be V Thevenins over R Thevenins plus R load. We know R load, while V Thevenins is unknown, R Thevenins is unknown. So we have two unknowns, which are V Thevenins and R Thevenins. How to calculate V Thevenins and how to calculate R Thevenins? Let's do step number 1. You can either choose step number 1 as calculating V Thevenins or calculating R Thevenins. I'm gonna just say, like, let's find R Thevenins. To find the R Thevenins, which is basically through turn of sources. Turn of sources. Any voltage source will be short circuit, any current source will be open circuits. Then just isolate network A and find R equivalent here. Let's have a look at network A. We have 2 milliampere, 6 milliampere, 4 milliampere. All of them are current sources. So this will be short open circuits. So let me initially draw network A alone, then I will apply turn of the sources. So I'm going to erase something. So first thing, I'm going to draw network A, which is 2 milliampere. Then here is 1 kilo ohm. I'm going to erase something later, so keep this in mind. Here is 2 kilo ohms. Here is 6 milliamperes. Then here is 4 milliamperes. So this is network A. What's the difference between this one and this one is I just removed the 1 kilo ohms resistor. This one and this one, they are the same, but remove the 1 milliohm because again, we will isolate only network A and forget about network B here. So then the terminals of network A and network B, those are calculated as A and B, and we need to calculate R equivalent here, but we need to turn off the sources. Turn off the sources, we mentioned here, any current source will be open circuits. Any voltage source will be short circuits. So here we have current source, we have current source, we have current source. But there is no voltage sources, right? So these current sources will be replaced by open circuits. So basically, I will erase them and keep it open circuits. That's how I apply the open circuit on it. So it will be like this. Okay? That's the circuits. Then now we have some unnecessarily wires. Like it's open circuit, open circuit. So let's remove them and redraw the circuits. 1 kilo ohms, 2 kilo ohms. Here is A and B. Then we need to find our equivalents. Okay? How to find our equivalents? Here is a node. Here is a node. Here is a node. Imagine there is a current going from A and back to B. Then 2 kilo ohms and 1 kilo ohms are sharing the same currents. Therefore, our equivalent will be 2 plus 1, then it will be 3 kilo ohms. Therefore, R Thevenin's equals to 3 kilo ohms. Okay? Now I'm done with the first unknown. Second unknown, V Thevenin's, we will do it through the open circuit tests. So basically, I'm going to draw network A again, and also I'm going to make the terminals of network A as open circuits, then we can calculate the voltage. So let me draw it again. Here is 2 milliamperes, 1 kilo ohms, 2 kilo ohms. Here are the terminals A and B. So we'll say plus minus V open circuits. Here is 6 milliamperes. Then here is 4 milliamperes. They will go here. Okay? Now, we need to do, what we need to do is to calculate V open circuits. Let me make it more organized. Which is basically the voltage here at the terminals A and B. How to calculate the voltages? So basically we can do KVL, KCL, Ohm's law. Since it's open circuits, the best thing to do it is only KVL, because we cannot apply Ohm's law at terminals A and B, right? So the only thing that we can do is to do KVL. So KVL, we can do KVL at this loop. So let me label the voltages as, and label the currents. So I'm going to assume the currents here as I1, the current here as I2. Then basically we will say about the voltages here plus minus V1, here plus minus V2. If we do KVL at loop 1, V2 is unknown, V1 is unknown. How can I calculate V2 and V1? Basically try to find I1 and I2. If we know how to calculate I1 and I2, then we can calculate V1 and V2. How to calculate I1 and I2? Try to do KCLs. Let's do, to calculate I1, keep in mind I1 will remain flowing here. Why? Because it will not split here, because here the current equal to 0. So I1 will remain here. So we will say, let's do KVL or KCL here. Do KCL. And let me call this node node 1. That's node 1. So this is node 1, KCL. I can call this one as I source 1, I source 2, I source 3. So KCL at node 1, the sum of leaving currents equals to 0. Therefore, IS2 is entering, therefore it is negative. Negative IS2. I1 is leaving, therefore plus I1. Then I source 3 is entering, therefore minus IS3 equals 0. Therefore I1 will be IS2 plus IS3. Then it will be IS2, which is 4 plus 6. Then it will be 10 milliamperes. The next thing is to calculate I2. So we can calculate I2 by doing KCL at this node. I can call this as node 2. So to do KCL at node 2, I'm going to write it here. KCL at node 2, the sum of leaving currents equals to 0. Therefore, IS1 is entering, negative IS1. IS2 is leaving, plus IS2. I1 is entering, so minus I1. I2 is leaving, plus I2 equals 0. Therefore, I2 will be IS1 minus IS2 plus I1. So it will be as, I think the current will be the answer 8 milliampere, I2. So we know I1, we know I2. Then we can calculate the voltages. So we will say that V1 will be I1 times R1. Then it's going to be as I1 10 milli times R1, which is 2 kilo. And then the answer will be 20 volts. Then V2 will be I2 times R2, which is going to be as 8 times 1 kilo. So the answer will be 8 volts. After that, we can do the KVL, loop 1, which is going to be negative V2, negative V1 plus V open circuit equals 0. Therefore, V open circuit equals V1 plus V2, 20 plus 8. So it will be 28 volts, or in other words, this is V open circuit. Then now I just calculated V Thevenin's, or actually this is V Thevenin's. I know V Thevenin's and R Thevenin's. So next lecture we will continue on this. Keep in mind there will be a quiz. Thevenin's circuit is not included. So chapter 3 is not included. The quiz will be only on chapter 2.